All right. So just a quick reminder that we have the first lecture quiz on Thursday. So the quiz will be held it'll be available at 8:15 and it's due at 9:30, I believe, it's due at 9:30. And that includes photos of your answers being uploaded to CrowdMark and submitted. So there's some baked in time to the actual writing time for photo submission and that sort of thing. The quiz, there's practice problems for the first quiz available on the course website. They're in the course content folder. The quiz covers lecture sets 1, 2, 3. So it's essentially a review style quiz covering topics from the end of stat 151. And I will send out another reminder via email about the quiz before. I'll send out a few more details regarding accessing the quiz. Hopefully it won't be an issue, but everyone will get an email inviting them to CrowdMark, and then they'll be able to go onto the CrowdMark page and access the quiz. There are always a few students that have trouble accessing it, so I'll send out, I have a little video that details another way that you can find the quiz, just in case you're having trouble getting to it through the link. And that's pretty much it, I think, in terms of getting ready for it. So again, I'll send out another email reminder beforehand. It's on Thursday, mainly during class time. There's about 15 minutes from 8 to 8:15 before the quiz starts, where I'll do a little bit of teaching. I'll probably work through an exercise or something, depending on where we are in the notes. And I will be available for questions in the office hour room during the quiz. Yeah, that's pretty much it, I think. Does anyone have any questions? Okay. All right, so if there are no questions, then we'll continue to work through lecture set number 5. We started lecture set number 5 on Thursday. It's essentially 2 major components, but there's 3 different topics in the lecture set. The first topic was residual analysis. So residual analysis is our main, or probably the most common technique for checking the normality and constant variance assumptions in ANOVA experiments. So we can use residual analysis for the one-way ANOVA and for the other types of ANOVA that we're going to study in this course. The process of computing the residuals is fairly straightforward. You just take the difference between the observed quantity and its expected value. So there's an example of this in lecture set number 5. But for the most part, this won't be something that we do by hand. We will typically just use SPSS to compute the residuals. And then we will just have to submit the residuals to either a normal probability plot or whatever method of testing for constant variance you're using for the assignment at hand. Because again, there's actually many different ways that you can test that constant variance assumption, ranging from statistical hypothesis tests to side-by-side box plots. Following the discussion of residual analysis, we started talking about contrasts. So this is the last part of assignment number 3. So the final question on assignment 3 requires the construction of an ANOVA table based off the summary statistics that are given. And then from that, we are tasked with setting up a population contrast. So this is an example of said contrast. What we are doing right now is essentially learning how to structure the contrast. So we're taking a written explanation of what it is that we want to compare, and we are turning that into a statistical, we will turn that into a statistical hypothesis test about that quantity. The quantity that designates a contrast is gamma, which is this symbol shown here. So I defined this last time, but just as a refresher, this is gamma. So gamma is like mu. It's just a population value. You can see from the expression given in A, gamma is a combination of the means in the experiment. So we have 4 means in this particular experiment, and we are combining them together to build what is called a contrast. And then what we're going to do is structure a hypothesis test about that contrast directly. So it's not all that different from building a hypothesis test about, 2 means or an ANOVA hypothesis about 4 means, for example. But what it allows us to do is directly compare the means within the experiment. Once we finish our discussion on contrast, I will introduce the multiple comparisons. The multiple comparisons are essentially a special type of contrast, but they are very common. It's a very common set of testing that takes place after the ANOVA. Because again, when we use an ANOVA at the end of the test, we don't actually know, well, if we reject the null hypothesis from an ANOVA, we don't know where the differences lie. So the contrast multiple comparison tools allow us to determine where those differences are actually located. All right, in the first illustration that we finished last class, we had set up a contrast that compares the average body length of minke whales entangled at depths of 0 to 99 meters to the whales entangled at 150 to 199. Okay, so we have 4 means. Each mean is designating a 50-meter spread or a 50-meter range of depths. We wanted to compare mu1 and mu2's average to mu4 in this particular situation. So essentially what we need to do are find coefficients for mu1 and mu2 and mu4 that create the average of the first 2 means, and then incorporate the last mean such that the sum of those coefficients is 0. So again, a contrast is a linear combination of the means where the coefficients are equal to 0. So the C's have to add to 0, where the sum of the coefficients is 0. So the C values have to add to 0, and we can't transform the means in any way. All right. So in this situation, we wanted the average of mu1 and mu2. So that leads to C1 and C2 being a half. And then we wanted to compare that to C4. So a half plus a half is 1. So we let C4 be -1. A half plus 0 minus 1 is equal to 0, which is what we wanted. So that gives us gamma equals 1/2 mu1 plus 1/2 mu2 minus mu4. Okay, so we're going to look at 2 other examples to try and familiarize ourselves with this process. In B, we have set up a population contrast that compares the average length of minke whales entangled at depths of 0 to 149 meters to whales entangled at 150 to 199 meters. Okay, so very similar problem to the first one, except that we're incorporating all of the means now. Okay, so we have gamma is equal to C1 mu1, C2 mu2, C3 mu3, C4 mu4. So we want average of mu1, mu2, mu3 versus mu4. So the average of mu1, mu2, mu3 is mu1 plus mu2 plus mu3 divided by 3. Okay. So it's a very similar problem to the first one. Instead of taking the average of 2 means, we now have the average of 3 means. So if we want the average of 3 means, we have to add those means together and divide by the number of means. So in this case, mu1 plus mu2 plus mu3 divided by 3. Right? Okay, so now what we have to do are set up the coefficients to make this computation work out. So we're going to have C1 equals C2 equals C3 equals a third. All right. We need the 4 C values to add to 0. So that means that we would let C4 be equal to -1, right? 1/3 plus 1/3 plus 1/3 is equal to 1 minus 1 is equal to 0. Okay, so therefore we have gamma is equal to 1/3 mu1 plus 1/3 mu2 plus 1/3 mu3 minus mu4. All right. Any questions? Right. Okay, in part C, it says, set up a population contrast that compares the average body length of minke whales entangled at depths of 0 to 99 meters to whales entangled at depths of 100 to 199 meters. Okay, so in this situation, we're going to be comparing the average of the first 2 depths to the second 2 depths. So again, we have gamma equals C1 mu1, C2 mu2, C3 mu3, C4 mu4. Okay. And then we want the average of mu1 and mu2 versus the average of mu3 and mu4. Okay. So that means for this test, we can let C1 and C2 be a half, and we can let C3 and C4 both be negative halves. Right, so now we have a half plus a half minus a half minus a half, which would be equal to 0. So that means that gamma is going to be 1/2 mu1 plus 1/2 mu2 minus 1/2 mu3 minus 1/2 mu4. Right. Any questions? All right, so now that we understand how to set up a contrast, what we are going to do is learn how we can build a hypothesis test and build a confidence interval about the contrast directly. So the idea here is we want to ask a question about gamma, or we want to build a confidence interval for gamma. So what we are doing is conducting inference about the population contrast directly. So this process is going to follow very closely what we had done in lecture sets 1 and 2. Maybe more so in lecture set 2 because of the form of the interval and the form of the test. But this is not all of that different from what we have seen in our study of inference and hypothesis testing so far. Okay, first, if we want to conduct inference about gamma, which is the population contrast, we need an estimate for that contrast. We call the estimate little c. Okay, so little c is to gamma what x bar is to mu. Right? So little c is simply an estimate of gamma. It follows that little c can be computed directly from our observed data, right? So little c would be c1 times x1 bar plus c2 times x2 bar plus c3 times x3 bar, all the way up to ck times xk bar, right? So it's just taking the sample means and constructing an estimate of the contrast using the coefficients that we built for gamma. Okay, contrasts typically follow one-way ANOVA experiments. The one-way ANOVA assumes that all of the variances in the population are equal. So if all of the variances in the population are equal, in each of the populations, are equal, then all of the standard deviations would be equal as well, because standard deviation is the square root of variance. So under the assumption of equal variance or equal standard deviation, which is what this part is indicating here, okay? We can show that the mean of the sample contrast is gamma, and the variance of the sample contrast is sigma squared. So a common estimate for the variance multiplied by C1 squared over N1 plus C2 squared over N2, all the way up to CK squared over NK. Right. To estimate sigma squared, we use what is called a pooled estimator. So little sp squared. Little sp squared is the same thing as the mean squared error from an ANOVA. Okay, so these are equivalent measures. So then we can write that the standard error of the sample contrast is the square root of the MSE multiplied by the square root of C1 squared over N1 plus C2 squared over N2, all the way up to CK squared over NK. So basically, when we are running inference about the contrast, we have estimate minus gamma divided by the standard error of the estimate. And this is the same form we've had for all of our different hypothesis tests and confidence intervals. Any questions so far? All right. So we can show that the population contrast is a linear combination of the means. If the means are normally distributed, then the contrast is also normal. So this is a property of normality. Basically, if you add normal values together, the sum of those values is still normal. So if we replace sigma squared with the MSE, which is what we are going to do in our hypothesis test, we can show that the test statistic is going to be a student T random variable on n minus k degrees of freedom. So basically, we're learning a new t-test. That's what this boils down to. So instead of using a test about one mean or a test about two means, we can do a contrast about multiple means, and it still is a t-test. Okay, and the test statistic is going to be the estimate minus gamma over the standard error. And it now has n minus k degrees of freedom. So that's an important point because we want to make sure we're using the right degree of freedom in our test. Okay, so we're going to look at the structure of the interval in the hypothesis test momentarily. Before we do that, I'll just note that the assumptions of the test for the contrast are the exact same as that of the one-way ANOVA. Essentially, contrasts typically follow ANOVA experiments. So if you've checked off the assumptions for whatever ANOVA experiment you are working on, then the assumptions for the contrast will follow from that. So we don't typically need to check the assumptions of the contrast directly. We would usually have run an ANOVA first, check the assumptions for the ANOVA, and then we're doing the contrast after those assumptions have been verified. Any questions? Right. Okay, so if we want to build a confidence interval for gamma, it's the same three steps. The examples will be coming up. Yep. Okay, so if we want to build a confidence interval for gamma, it'll be the same three steps that we've seen for any confidence interval. So we start by finding a t-value, and then on the second step, we construct the interval. So the form of the interval is shown here. So it's little c plus or minus the t-value multiplied by, I have SP here, but remember that little sp is the square root of the MSE. So we can pull that from the ANOVA table directly. And then we have to interpret the interval. Okay, so pretty much the same three steps we've seen throughout the class. Okay, our hypothesis test will be carried out in 6 steps. Just like any hypothesis test, we have a variety. We have 3 different types of hypotheses that we can use. So for example, we have the two-sided test about gamma. So gamma equals 0 versus gamma different from 0. And then we have both of the directional tests. So we can test that the contrast is greater than 0, or we can test that the contrast is less than 0. Most often we will be using two-sided tests for contrast, because usually if you want to compare the average of this quantity to the average of the other quantity, you're usually looking for a difference. But you can technically build directional tests as well. So we have to pay close attention to what the questions are asking us when structuring these types of contrasts. So step 2, significance level. Step 3, test statistics. Step 4, p-value or critical value. Again, these are t-tests. So the critical value and p-value will be done in the usual way using the student t-table, but it's on n minus k degrees of freedom rather than n minus 1 or n1 plus n2 minus 1, that sort of thing. Okay, so then we make a decision and then we interpret the results. All right, so we'll look at an exercise now that sort of works through all these different ideas at the same time. So we're going to refer back to the Minke whale exercise. So at the end of, or in lecture set number 4, we did an example where we illustrated how the one-way ANOVA would work for the minke whale data set. So from that illustration, we found the mean squared error was 0.9. We had an F value of 13.742, and then our sample sizes are also given here. So from the ANOVA, we determined that there was evidence of a difference. So now what we're going to do is start building contrast to see if we can locate some of the differences, and then we'll talk about a more efficient way of determining where the difference lies following from that. Okay, part A says, suppose researchers wish to determine if there is evidence that the average body length of minke whales entangled at depths of 0 to 99 is different from that of whales entangled at depths of 100 to 199. We're going to run this test at the 5% significance level. In part A, it's saying give the null and the alternative and estimate the standard deviation of the contrast. Okay, so what I'll do here is I'll actually work through the first 3 steps of the test. And then in part B, we'll do the next 3 steps of the test. I split these up into different parts to kind of try and tackle conceptual aspects of the hypothesis testing procedure, but I think it'll probably be better to just go through the steps of the test directly so that you can see how they would unfold. And then from that, we can talk about the corresponding confidence interval. Okay, so first off, let's just make sure we know what we're testing for. Now, we're using the same data set that we used in lecture set 4. Okay, so we're going to assume the assumptions are all intact, and we're just going to focus on working through the test. Okay, so we want to check evidence okay. So we want evidence, average body length of whales at 0 to 99, different from average at 100 to 199. Okay. So first off, so the contrast that we are going to be working with here is one of the contrasts that we had just set up when we started the lecture set. So we're comparing the average of 0 to 99 to the average of 100 to 199. So this is going to be 1/2 mu1 plus 1/2 mu2 minus 1/2 mu3 minus 1/2 mu4. Okay. And then you can refer to slide 12. Okay, so you can refer, and then you can refer to slide 12 for that declaration. Okay, so we want to know, basically what we're doing here is we're testing whether or not the contrast is different from 0. Okay, so to determine if average of mu1 and mu2 is different from average of mu3 and mu4, test H0 gamma equals to 0. All right, so let's think about that. Why are we able to do this? Okay, well, if we have gamma equals to 0, that means that we have 1/2 mu1 plus 1/2 mu2 minus 1/2 mu3 minus 1/2 mu4 equals 0, right? So if that's the case, then this thing can be written as 1/2 mu1 plus a half mu2 equals a half mu3 plus a half mu4. Okay, so essentially, we want to compare the average of mu1 and mu2 to the average of mu3 and mu4. So the contrast, 1/2 mu1 plus 1/2 mu2 minus a half mu3 minus a half mu4 being equal to 0 results in the average of mu1 and mu2 being put against the average of mu3 and mu4. Right? So this contrast is allowing us to compare the averages of the depths that we are interested in. All right, so therefore, on step 1 of the hypothesis test, we're going to have H0 gamma equals to 0 versus HA gamma different from 0. All right, and then on step 2, we would have 0.05. All right. Okay, on step 3, we would then have our test statistic. So the test statistic is little c minus gamma divided by the standard error of little c. Okay, so little c is going to be 1 over 2 x bar 1 plus 1 over 2 x bar 2 minus 1 over 2 x bar 3 minus 1 over 2 x bar 4. Right? So this is going to be 1 over 2 times 4.49 plus 1 over 2 times 5.06 minus 1 over 2 times 5.75 minus 1 over 2 times 5.99. Okay, and then one sec, I'll reference that, which is equal to negative 1.095. Okay, and then x bar 1 to x bar 4 from set 4 slide 8. Right. So the means that I'm using here, these are from the previous lecture set. I just forgot to write them down in the notes. Okay, so you can see little c is an estimate of gamma. All we're doing is we're taking the structure of gamma and we're just replacing mu with x bar. So now we have an estimate for gamma. Yeah, Diana, that would work as well. Yeah, same thing. Any other questions? All right, so the standard error of C is going to be the square root of the MSE multiplied by the square root of C1 squared over N1 plus C2 squared over N2 plus C3 squared over N3 plus C4 squared over N4. Right. So this is going to be 0.9 multiplied by 1/2 squared divided by 39 plus 1/2 squared divided by 20 plus negative 1/2 squared divided by 28 plus negative 1/2 squared divided by 14. Right? And that gives us 0.2027964. So then we have negative 1.095 minus 0 divided by 0.2027964, which is negative 5.400. And then this part here is technically what A is asking for. Right. Any questions? Okay. So in part B, it says for the test in A, a test statistic of t equals negative 5.400 was found. So we actually went through the process of computing that so we can see where it came from. What is the result of this test? Okay, so hint, perform step 5 to step 6 of the experiment. Okay, well, I mean, to perform step 5, we have to do step 4 anyway. So we're going to basically just continue with the hypothesis test here. Okay, so on step 4, we can take either the p-value or the critical value approach, right? We're running a t-test. So everything from this point is going to be exactly like it was before in terms of determining if we have evidence for or against the null. So we can take a critical value approach or a p-value approach. If we take a critical value, right, we start by sketching out our curve. Right, so here's my student T curve. Okay, we're running a two-sided test here. So I'm going to have a critical value in both tails. Okay. All right, so this is going to be a t-value alpha over 2 n minus k degrees of freedom. So this is a t-value on 0.025. And then we have n minus k. So we're going to add all of the sample sizes together and subtract the number of means, right? So in this case, we should have 101 minus 4. Okay, so this is going to be a t value on 0.025 and 97. All right, so now we go to our t table. Okay, so we have 0.025. Okay, so we have 97 degrees of freedom. We don't have 97 in the t table, so we always round down. So that gives us 1.985. Okay, so this value here is 1.985. So that means that in the lower tail, we have negative t 0.025, comma 97. Which is negative 1.985. Okay, and then the test statistic is negative 5.4. So that'll be somewhere here. Right, so the test statistic is clearly in the rejection region, so we can reject H naught. All right. Okay, if we took the p-value approach, it's the same idea. So we start by sketching out our curve. Okay, so now we have to consider the test statistic in both tails because it's a two-sided test, right? So same process that we have gone through with all of our t-tests. So the p-value is going to be the probability that t is less than negative 5.400 plus the probability that t is greater than 5.400. This is the same thing as 2 times the probability that t is greater than 5.400. Okay, so now we will go to our t table. All right, so we have 95 degrees of freedom in this particular situation. Well, we have 97 degrees of freedom, but we're using the 95 line because we don't have the 97 line in the t table. We're looking for 5.400. We can see that that's bigger than the biggest listed value. So therefore, the p-value, or the area rather, in one tail is going to be smaller than 0.005. So we can say, since this probability is less than 0.005, then the p-value is less than 2 times 0.005. P-value is less than 0.01. All right. Okay, so then on step 5, we would reject H0. And on step 6, we would say at the 5% significance level, the data provide
sufficient evidence to suggest that the average length of minke whales trapped at 0 to 99 meters is different from that of whales trapped at 100 to 199 meters. Okay.
Ugh, my hand hurts. Okay, so pretty standard hypothesis test, just built about the contrast. Any questions? All right, so in part C, it says, will a 95% interval, a confidence interval, have negative bounds, positive bounds, or one negative, one positive? Explain. Okay, so for this question, I mean, one way you could do this is just build the confidence interval, but the confidence interval is going to be built in the same 3 steps that any other interval is going to be constructed in, right? So for example, if we built the interval, we would have T alpha over 2 n minus k. So this is going to be T 0.025 97. So then we're going to use the estimate from the T table that we used in the previous question. So that's going to be the 1.985. Okay, so we have the same critical value here. Okay, so we have the same critical value for the confidence interval and the hypothesis test. So when we have the same critical value for an interval and a test, the results are going to agree. All right, that's the first thing. Now, just for clarity, if we were to build the interval, you would have C plus or minus T 0.02597 multiplied by the standard error of C. Okay, so you would just have to plug those 3 values in. We don't need to do that here because we know that the interval and the test are going to give the same conclusion. All right, so since critical value is the same for CI / hypothesis test, results will be the same. Okay. So we rejected the null hypothesis in the hypothesis test. So will the confidence interval contain 0 or not contain 0? Any ideas? Okay, good. So since we rejected H0 gamma equals 0, the CI will not contain 0. Okay, now the question asks, will the bounds be negative or the bounds be positive? We know that 0 is not in the interval. So if 0 is not in the interval, you have to have two bounds that are the same side, the same sign, right? So if you have a negative and a positive bound, that means that you have to cross 0. So this is either going to be two negatives or two positives, right? The sign of the bounds will match the sign of C and T. Right? So if we reject the null hypothesis, the confidence interval is going to have two bounds whose sign is the same, whose sign, anyways, the sign of the bounds on the confidence interval will be the same as the sign of little c or the test statistic. So in this case, little c is negative and the test statistic is negative. So therefore, the confidence interval is going to have two negative bounds. Okay. And you can actually verify that by constructing the interval. Right? So if we take our values from the interval, we have negative 1.095 plus or minus 1.985 times 0.2027964. Right? And if we put those together, we get approximately negative 1.498 to negative 0.692. Right? So 2 negative. That's okay. Any questions? All right. Okay, so if there's no questions, that brings us to the end of the discussion on contrasts. All right. Now, as a reminder, the general idea, a contrast is a tool that allows us to compare any number of means within the data or populations of interest. I guess within the data set of interest or within the problem of interest. The contrast, in order for the contrast to be valid, you have to have a linear combination of the means where the coefficients sum to 0, right? So we had in our previous illustration, C1 plus C2 plus C3 plus C4 equals 0, and we had no transformation to the means. So the means have to be linear and they can't be multiplied or divided by each other. They can't be square rooted. They can't be exponentiated in any way. They just have to be linear combinations where the coefficients add to 0. When we run an ANOVA, we get out a result that basically says a difference exists among the means. Okay, so determine where that difference lies. It's the most efficient, or the tool that we use to find the difference is a special kind of contrast called a multiple comparison. And basically what the multiple comparison does is it just takes all possible combinations of the means or all possible pairs of means, and it builds contrast among those pairs. So the multiple comparison is a special type of contrast where you only are comparing two means at a time. So you'll always have one coefficient that's a positive one coefficient that's a negative one, all other coefficients are 0. All right. Now, multiple comparisons can be exhaustive. Depending on the number of treatment groups or the number of population means, which we call little k, there are going to be choose 2 different combinations within any given experiment. All right. So choose 2 is basically a value that's going to scale up very quickly. So as k increases, this number gets large very quickly, right? Now, when we're setting up multiple comparisons, we have to distinguish between 2 types of error. Well, we have to distinguish between 2 types of type 1 error. In all of the hypothesis tests that we have considered this semester, on step 2, we always specify alpha. Alpha is the probability of type 1 error by definition. So essentially what we are doing when we build a hypothesis test is we are declaring our accepted amount of type 1 error. When we run a multiple comparison, the probability of a type 1 error will compile very quickly. So it'll get very large very fast. In order to control it, we have to distinguish between what we call the individual type 1 error. So this is the type 1 error of each multiple comparison, and the experiment-wise type 1 error, which would be the type 1 error of the entire process that we are undertaking. Essentially, multiple comparisons will almost always follow a one-way ANOVA or a ANOVA of some kind. When we run the ANOVA, we declare the experiment-wise error. So we're going to say we have an ANOVA procedure. We're going to run the ANOVA at the 5% significance level. And then that is the experiment-wise error. When we run the multiple comparison, we have to adjust the experiment-wise error such that the individual or such that the type 1 error for each of the different multiple comparisons does not go beyond that experiment-wise error. Okay. So more specifically, when we run multiple comparisons, essentially what we're doing is performing a hypothesis test or building a confidence interval for every single pairwise comparison that exists within our data of interest. Most often we use confidence intervals because it's faster to interpret. So we can build the interval. If the interval does not include 0, we have evidence of a difference. If the interval includes 0, no difference, right? So it's a quick check. For every interval under the multiple comparison, we have to use an individual error. So we have to adjust alpha for each of the different multiple comparisons. The reason, again, is because since the experiment-wise error is going to be the type 1 error for all of the different comparisons, if we do not compensate and reduce the experiment-wise error for each interval, then the type 1 error is going to go beyond what we actually specified. So essentially what I'm trying to say is when we declare alpha in the one way in an ANOVA, this is the overall accepted type 1 error for the entire experiment. Okay, so we don't want to go beyond this value. In order to ensure that we do not exceed that specified value, we have to adjust the significant or the alpha value, the probability of a type 1 error for each individual interval. Okay, so that alpha subscript I is the individual type 1 error rate for each interval or hypothesis test in the set of multiple comparisons. And we adjust it so that we do not go over alpha subscript E. Okay, that's the goal. Okay, so how do we actually adjust this value? There's a number of different ways to adjust. Basically, you specify alpha E. So this is going to be the value we set when we start the experiment. And then we can adjust the alpha E for each of the multiple comparisons using, for example, the Tukey HSD procedure, the Tukey-Kramer procedure, the Scheif procedure, or the Bonferroni. In our situation, we're going to use the Bonferroni because it's the easiest one to explain and to digest. But all of these different procedures do the same thing. They just adjust alpha E to create an alpha I such that you do not exceed alpha E. All right. Any questions? All right. So we'll look at an example so we can get a better understanding of what it is I'm trying to say. So we start off by specifying alpha subscript E, which is usually just the significance level for the ANOVA, for example, right? So we're going to run the ANOVA. For the ANOVA, we're going to have an alpha. That's going to become the experiment-wise error rate. Okay. Then we compute the number of multiple comparisons that we have to make. So again, little m is equal to k choose 2. All right, so which is the same thing as kc2. Okay, so this is just the combination operator. And this is something you can do on your calculator directly in one step. This is a built-in function. I suppose it would be worth it just to say too, like this is k factorial over 2 factorial k minus 2 factorial. Okay, so if you don't remember the combination operator, but you remember factorials, this is what that is. Okay, so you compute the number of comparisons you're going to make. Then you compute what we call alpha star. Alpha star is the same thing as alpha I. Okay, so alpha star is equal to alpha I, and the alpha is the alpha E. Okay, so we can say, basically, when we're using a Bonferroni, we're just saying alpha I is alpha E over 2m. Sorry, let me just check something very quickly here. Okay, so basically we have alpha I is the alpha E over 2 times M, right? So it's a very easy adjustment. You specify the experiment-wise error rate, and then you divide by 2 times the number of comparisons that you want to make. Right? And that's essentially the Bonferroni, which is why we use it, because it's very easy to explain and to understand. It's like, okay, you're just taking overall error and dividing it by the number of comparisons. It's easy. All right, then what we have to do is build the margin of error for each comparison. So the margin of error is the t-value or a t-value on alpha star, which is alpha I, n minus k degrees of freedom over the square root of MSE times the square root of 1 over ni plus 1 over nj. Okay, and then in step 6, we have like summarize using bar notation and this sort of thing. This part, the 6th step, there's a lot of different ways to summarize the result. Like you can basically just check off which intervals have a 0 and which don't, and then say that this is where the difference lies. I'll show you the bar notation just for completeness sake, but there are multiple ways that you can do this, is the point. Okay, so for the minke whale data set, we are going to use multiple comparisons to determine where the differences lie among those 4 different depth levels. Okay, so we rejected the null hypothesis that the means are equivalent. So back in lecture set 4, we ran the ANOVA. From the ANOVA, we found evidence of a difference. And now what we are interested in doing is determining where the differences actually exist. So we're going to do this using a Bonferroni procedure. Okay, so following the process given on the previous slide, we start by specifying our overall experiment-wise error. So let's say we use 0.05. Okay, then we compute the number of comparisons. So on step 2 here, we have little m is equal to 4 choose 2. Okay, so this is 4C2, right? So again, this is something you can just do in your calculator directly, but just for clarity, just for completeness, this would be 4 factorial over 2 factorial times 4 minus 2 factorial. Okay, so this is going to be 4 factorial over 2 factorial times 2 factorial. So this is going to be 4 times 3 over 2, which is 6. Okay, again, you don't need to write it all out. You can just compute it directly in your calculator or using whatever type of calculator you're using. But this is how you would find little m. So 4 choose 2 is 6. That's the idea. All right. On step 3, we compute alpha star. So this again is going to be alpha I is equal to alpha E over 2 times m. So this is going to be 0.05 divided by 2 times 6, and that's 0.00416. Okay, so this is the alpha value that we're going to plug in to our multiple comparison of interest. Okay, now what we have to do is compute the margin of error. Well, on step 4, you put the means in ascending order, but that again doesn't really matter. So now what we need to do is compute the margin of error for each of the different comparisons. All right, so for example, I have the margin of error for comparing mean 1 to mean 2 shown at the end of slide 25. So this is going to be our t-value multiplied by the square root of 0.9 divided by the square of 1 over 39 plus 1 over 20. Okay, so this is the comparison for 1 to 2. Okay, so this t-value I found using statistical software, so I was able to get an exact value here. if we were using the t table, we would just have to round to the closest value because we don't really have a choice. So if using the t table to find t 0.00416, comma 97, we would use t 0.005, comma 95. Okay, because that would be the closest that we can get to the actual value. So that would be 2.629. So a lot of the time when we're doing these things on assignments, we might not be, or on a test rather, on assignment, you could get an exact value because you have access to software. But if on a test, you wouldn't have the software in front of you to find exact values for the t value. So you have to use the table. In that case, you have no choice but just to round to the most appropriate value. So in this situation, the most appropriate value would be the t on 0.005 and 95. Okay, so any questions? Okay. Okay. All right, so we have to build a margin of error for each of the different comparisons of interest to us in this experiment. So we want to compare the 6 different means. So we want to compare the mean at 0 to 49 to the mean at 50 to 99. We want to compare the mean at 50 to 99 to 100 to 149, the mean at 0 to 49 to 100, 149, etc. So in this first table under 5, these are all of the different margins of error that we need for this particular experiment. Okay. So we looked at an illustration of the first comparison, right? So we showed on the previous slide where 0.703 came from. Okay. So we have here E12 0.703 is the comparison of 0 to 49 to 50 to 99. Okay, so it's the same process for the other means as well. So for example, let's just look at this illustration here. So for 0.633, okay. So for this value, we would have E13, right? So this would be, following from the previous illustration, our t value on 0.00, 97 divided by 1 over 39
plus 1 over 28.
So you can see what's happening here is we're actually just shifting the sample sizes in each of the margin of error comparisons for this particular example. This would be the same idea here. So if we were to compare so E12, E13, so E23, this would be a t-value 0.0041697. And now we would have the sample sizes for the second and the third group. Okay, so that's going to be 1 over 20 plus 1 over 28. All right. So very similar calculation for all the margins of error. We just have to switch the sample sizes in this particular illustration because we have different sample sizes for each group. But actually, in the situation where the sample sizes are the same, the margin of error is going to be the same for all comparisons as well. Okay. So the last thing I'll do is I'll just make a note. So if E is less than the absolute difference, so if Eij is less than the absolute difference between X bar I and X bar J, then a difference exists. Okay. So the last thing we need to do here is basically just compare the absolute differences between the means to the margin of error. And if that absolute difference is bigger than the margin of error, we can say that there's a difference between the means of interest. Right? So I'll go over that part. I'll go over this part at the start of class on Thursday. So I'm going to lecture for about 15 minutes from 8 to 8:15 on Thursday. And then the quiz will release and you guys will have the rest of the time to finish that. Again, I'll send out reminders about the quiz before Thursday. I'll also send confirmation of accommodation to anyone that requires it. So if you don't hear from me by Wednesday evening, please let me know. And otherwise, I'll talk to you guys on Thursday morning for a bit, and then the quiz will start, and then I'll talk to you after the weekend. So have a good couple of days, and I'll see you then.